Hi, and welcome to Index Law's The Contextual videos. And in this video, we're going to talk about scientific notation. And so in this video, we'll talk specifically about what scientific notation is and how we represent very large or very small numbers in this way. We'll do some problems involving manipulating scientific notation through some of our operations. And we'll also consider the use of significant figures briefly so that you've got that understanding behind you as well. So first of all, what is scientific notation? So scientific notation is where you take a really large number. Let's say, for example, 7287018924618. So that's quite a large number. There's the thousands, the millions, the billions, trillions. 7,287,000,18,924,618. And as you can see, it's a little bit of a hassle to write that number down. So what we can do instead is we can do a little bit of rounding, and it will be some significant figure rounding, and some use of scientific notation to write this down in shorter terms. So this number actually becomes 7.287 times 10 to the power of 12. And I'm about to explain why. Now, of course, I have rounded, so it might be more appropriate for me to do these little curly equal signs, which means is approximately equal to signify that I've done a little bit of rounding there. So let's have a closer look at scientific notation. Scientific notation should come to you in this form: a times 10 to the power of b. Now, in this case, the a will always be a number that is greater than 1, greater than equal to 1, and less than equal to 10. So a should exist between 1 and 10. The idea is to bring this down to be a simple one-digit number with perhaps some decimal points. B, on the other hand, will be a positive or negative whole number. And of course, the base will always be 10. Because we count base 10, it works with our number system, and if you try this with another base, you'll find it's quite a hassle. So we've got a times b to the power of 10. Now let's look at a really simple case. Let's say we talked about the number 3,270,000. Now I'm going to take out factors of 10 and have a look at how this is constructed. So I can write this down as 327,000 times 10. And I can write this down as 32,700 times 10 times 10. So I've just taken another factor of 10 out. And I can write this down as 3,270 times 10 times 10 times 10. And I can write this down as 327 times 10 times 10 times 10 times 10. And you get the point with where I'm heading here. Ultimately, I can write this down as 32.7 times 10 5 times, which means times 10 to the power of 5. And of course, that means I can write this down as 3.27 times 10 to the power of 6. So I've taken out as many factors of 10 as I can. You'll note here that this is 10 and it equals 10. That's going to seem a little bit monotonous, but this is 10 squared and it equals 100. And this is 10 cubed and it equals 1000, and so on and so forth. So you get those powers of 10, which are nice easy numbers, and they work with our decimal system. So of course I can use the powers of 10 to actually analyse this a little bit differently. So let's take the number 3,270,000 and consider what is our largest factor of 10 we can take out without reducing this number below 1. So I could divide this by a million and I'd be left with 3.27 million. You can see that there is 3.27 million. If I divide it by 10 million, of course, I'll be left with 0.327. So I don't want it to go below. So I can divide this by a million. Now a million is 10 to the power of 6 and I get 3.27. So that's an interesting way to look at it. But better yet, let's have a look at this. The decimal point begins here. 3,270,000.0. I'm going to be able to move this decimal point and I'll be able to consider how many points it moves along the number. And of course, if you count those up, you get 6. So that power is really easy to generate just by looking at the number, moving the decimal point, or perhaps moving the number over the decimal point, until you get the decimal point to be after the first significant figure, after that 3 in this case. So we'll end up with 3.27 and 10 to the power of 6. So let's have a look at some examples of this. 7214 0000000. So in this case, I can clearly see this is going to be 7.214 is my most accurate case, times 10 to the power of, and my decimal will go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places up, so times 10 to the power of 10. So you can see what I've done now. I've developed a method that's quite easy in order to write my very large number in scientific notation. Now, what about small numbers? You can do this for small numbers as well. So let's take the number 0.000162. The same process applies. If I take this decimal and I need to move it down 1, 2, 3, 4, that will create 1.682. So this creates a situation where I'm moving down 4 places, and that gives me 10 to the negative 4. So 1.682 times 10 to the power of negative 4. So let's have a look at one more example. 0.0003789201947. So I've deliberately chosen a pretty obscure number, but you can actually see the number or the power of 10 that I need to use is quite low. Again, I've only moved this 1, 2, 3, 4 places. So my answer will be 3.7, and it's now about choosing the level of accuracy I want. So I may just go to 3.79 times 10 to the power of negative 4. Despite all these factors here, I don't actually have to move the decimal point that far. Now here's the really nice thing about scientific notation. In many applications, you'll need to multiply or divide very large or very small numbers. Now, the addition and subtraction in scientific form is a bit of a hassle. You have to turn it back into its original number, but multiplication and division, on the other hand, is really good. So let's take an example. 2.7 times 10 to the power of 16 times 1.5 times 10 to the power of 4. So here's a quick example for you. Now multiplying these means that I can rearrange those values because they're all just multiplied together. So I'm going to rearrange it to be 2.7 times 1.5 times 10 to the power of 16 times 10 to the power of 4. And the good thing here is that 2.7 times 1.5 can just simply be evaluated to be 4.05. And 10 to the power of 16 times 10 to the power of 4 becomes 10 to the power of 20. Because one of our index laws states that you add the powers as long as the base is the same. So we get 4.05 times 10 to the power of 20. Let's have a look at a second example. In this example, I've got 1.78 times 10 to the power of negative 3 times 5 times 10 to the power of 10. And so in this case, 1.718 times 5, and then times 10 to the power of negative 3 times 10 to the power of 10 will mean that I get 8.9, that's 1.78 times 5, times 10 to the power of 7, because I get negative 3 plus 10. And lastly, example number 3, 2.8 times 10 to the power of 8 divided by 7 times 10 to the power of 6. And this is going to wrap up a couple of little interesting facts. So first of all, let's write this down like a quotient. 2.8 times 10 to the power of 8 divided by 7 times 10 to the power of 6. So numerically, the 2.8 divided by 7 gives me 0.4 times 10 to the power of 8 minus 6. That's how we just divide powers. So this, of course, is 0.4 times 10 squared. Now, this is not currently in scientific notation because that 0.4 is too small. It needs to be between 1 and 10. So I'm going to write it down instead as 4, and then I'm going to multiply that by 10 to the power of negative 1. You'll note here that 4 times 10 to the power of negative 1 is the same as 4 over 10. And 0.4 is 4 over 10. And I'm going to multiply that by 10 squared. And this creates for me a situation where I have 4, which is in the right range, times 10 to the power of 1, negative 1 plus 2. And of course, sometimes scientific notation is a little bit ridiculous. In this case, 4 times 10 to the power of 1 is just 40, and we probably wouldn't use scientific notation. But if we divide these two terms, the answer is 40. And as you can see, apart from overworking it a little bit, that answer is quite easy to come by. So let's have a quick talk about significant figures. So here is a really small value, 0.00002917. Now this is, at the moment, rounded to 9 decimal places. And despite the fact there are 5 zeros after the decimal point, we have to say it's rounded to 9 decimal places. So when you're dealing with really large numbers or really small numbers, it's really hard to define the rounding that's going to take place. Similarly, let's have a look at another really large number, 32178937180012. So this number is 3,217,893,718,012. But realistically, if we're dealing with the trillions, then we might consider the thousands, or sorry, the numbers below 1,000, or even perhaps the thousands, or even perhaps the millions, somewhat insignificant. But we can't ask to round that number. That's the problem we're dealing with. I might actually think, for my calculations of my benefit, my purpose, and the simplicity of the problem, I might want to write that down as 3200,000,000,000,000. So this is where significant figures come in. It is rounding for any number, whereas our current form of rounding is just for those numbers close to the decimal point. So in this case, we have 2 significant figures. And in this case, we have 4 significant figures, sometimes called sig figs. So 4 and 2 significant figures. So this is how significant figures work. We get a number such as the 0.00002917, and let's say that was extended to be 3689218, and so on. And we move ourselves down to the first non-zero number, which in this case is 2. And from that 2, we highlight the number of significant figures we'd like. So we've got 2917. This will create 4 significant figures. We get the 5th figure, which in this case is the figure 3, and we use that to determine whether we're rounding up or rounding down. So 4 or below will round down, 5 or above will round up. And then we just create a string of zeros after as appropriate. Because this is below the decimal point, we don't need any additional zeros. 2917 is appropriate. If it was above the decimal point, we would need additional zeros. The only time zeros become really important and count as a significant figure is when they are inside the boundary of the 4. So in this case, when a 0 appears within 4 digits of the leading significant figure, then it would be important. So let's have a look at some examples of this. 1. 3817,219,0716. I'm going to do this one to 3 sig figs. So I go to my leading non-zero figure, which is 3. I write down my next 2 figures, 8, 1. I take my 4th figure, 7. That's going to round up. So I'm going to change this 8, 1 to an 8, 2 because I'm rounding up. And then I add zeros because in this case they are appropriate. So I replace every number with a 0. It's the same value, but I've rounded it to 3 significant figures. Let's have a look at question 2. 0.0007001724. And I'm going to do this one to 4 significant figures. Now you'll notice here that I've clearly made this deliberately so that we get to our first significant figure. We add on our additional 3 to make it 4 significant figures, and we take our 5th significant figure and use that as our rounding key. And in this case I get 0.000, these 3 zeros are still important for magnitude purposes, 7002, because that 7, the 5th significant figure, determines that we need to round up. Let's consider example 3, 582111748, and I'm going to round this one to 4 significant figures. So I take the first significant figure, I add on an additional 3, I take the 5th significant figure and consider whether I round up or down. In this case I round down 58210000. And my last example, 0.000005180461. And I'm going to do this one to 4 significant figures. So in this case I take my leading significant figure 5, I add to it 3 more additional significant figures, and I take the 5th significant figure and use it as a rounding key. So I am rounding down because it's a 4, 0.00005180. Now because I needed 4 significant figures, this 0 is still important. So it gives an indication of what rounding would occur should we take or do something else with it. And it's still important to have that 0 because it has been specifically asked for here. So there's significant figures and there's scientific notation. All the best.